Okay, picture this scenario. Larry, he's 30, rushed into the ER automobile accident.
Right.
And he's unresponsive. So they draw blood, send it straight to the lab, to Brianna, the tech.
Standard procedure in that situation.
And minutes later, Brianna gets a result. His blood pH, 7.30.
Uh-oh, that's low.
Exactly. Normals are like 7.35 to 7.45, super tight range. So 7.30 means acidosis.
And they figured out why.
Yeah, respiratory acidosis. His CO2 partial pressure was way too high, so Brianna flags it immediately.
Good catch. Critical timing.
And the ER team jumps in, gives Larry an IV with bicarbonate, aiming to raise that pH back up, clear his airway too.
Makes sense. Counteract the acid buildup.
And thankfully, not long after, his levels started normalizing.
Wow. That's quite the save.
It really is, and it all hinges on that one number, that pH reading. So how does that lab test measuring blood pH connect back to, fundamental chemistry?
That's the fascinating part, isn't it?
And what does it even mean for your body to be acidic or basic?
It shows chemistry isn't just beakers and labs. It's literally inside us, running the show. Life and death stuff, like with Larry.
Right.
So today we're doing a deep dive into acids, bases, and this idea of equilibrium. We're pulling insights from Timberlake's chemistry, an introduction to general, organic, and biological chemistry.
Okay.
And the mission here is really to give you a shortcut, a way to grasp these core concepts and see how surprisingly relevant they are to your health, the world around you.
All right, so understanding Larry's acidosis,
Yeah.
Where do we even start? What is an acid? Or a base, like fundamentally?
Good question. We can go back to Svante Arrhenius, way back in 1887.
Okay.
He gave us the first sort of modern definition, acids. They produce hydrogen ions, that's H+ when you dissolve them in water.
H+ ions, got it, like hydrochloric acid, HCl.
Exactly. HCl in water releases H+ micaid. Bases, on the other hand, they produce hydroxide ions, OH, in water. Think sodium hydroxide, NaOH.
Okay, H+ for acids, OH for bases. In water.
Precisely. And here's a key thing for you to understand. Because they produce these ions in water, both acids and bases are what we call electrolytes.
Electrolytes, like in sports drinks.
Sort of, yeah. It means they can conduct electricity when dissolved. And that electrical conductivity is absolutely fundamental. It's how your nerves fire signals, how your muscles contract.
Wow.
It's chemistry literally powering you right now.
That's wild. So the same chemistry that makes a lemon taste sour.
Citric acid, ascorbic acid.
Yep. Is also working away in my stomach digesting lunch.
Hydrochloric acid doing its job. Absolutely. These things are everywhere. Acids tend to taste sour. They can corrode metals.
Right.
Bases, often bitter, feel slippery. Think about soap or drain cleaner. Even antacids like milk of magnesia. They neutralize acids.
Naming them, is there a system, like hydrochloric acid?
Yeah, there is. Simple ones like HCl, where the anion is just one element, get hydro prefix and a high acid ending, hydrochloric. If it involves oxygen, like nitric acid, HNO3, or nitrous acid, HNO2, it depends on the polyatomic ion. Usually I for the common form, allergies for the one with less oxygen.
Ah, okay. And bases?
Bases are usually simpler, typically just named as hydroxides. Sodium hydroxide, potassium hydroxide.
So Arrhenius gave us a start, H+ and OH in water, but you said it gets more nuanced, especially in biology.
Exactly. The Arrhenius definition is great, but it's kind of limited to water. In 1923, Brunstad and Lowry came up with a broader definition.
Okay, what did they propose?
They focus on the transfer of the hydrogen ion. A Brunstad-Lowry acid is an H+ donor.
Okay.
And a Brunstad-Lowry base is an H+ acceptor. It doesn't have to produce OH ions itself. It just needs to be able to grab an H+ ion.
So it's about giving and taking H+.
Precisely.
And an important detail. That H+ ion, the proton, doesn't just float around freely in water. It's immediately grabbed by a water molecule.
Oh.
Yeah, water acts as a base in this case, accepting the H+ to form H3O plus M. We call that the hydronium ion. Hydronium, H3O plus arrow. So that's what's really in an acidic solution.
That's the key player representing the acid in water, yes.
Yeah.
H3O plus.
Okay, so it's like this chemical handoff, donor, acceptor.
Yeah.
Does this lead to something called conjugate pairs?
You got it. When an acid donates its H+ error, what's left behind is called its conjugate base.
Mm-hmm.
They're a pair, differing only by that single H+ arrow.
Example?
Sure. Hydrofluoric acid, HF. It donates H+ error, leaving behind the fluoride ion, F. So HF is the acid, F is its conjugate base.
Okay.
And conversely, when a base accepts an H+ error, it forms its conjugate acid. Water, H2O, accepts an H+ to become hydronium, H3O plus air. So H3O plus is the conjugate acid of the base H2O.
It's always a pair related by one H plus error. Makes sense.
And this flexibility leads to amphoteric substances.
For what?
Amphoteric means they can act as either an acid or a base, depending on what they're reacting with.
Like water?
Water is the classic example, but bicarbonate, HCO3, that ion we mentioned from Larry's IV, that's another crucial amphoteric substance in your body, super important for balance.
This is getting interesting. Now, you mentioned strength earlier. Not all acids or bases are the same, right? What does strength actually mean here?
Right. It's a really critical distinction. Strength isn't about, like, how corrosive something is necessarily. It's about dissociation.
Dissociation.
Breaking apart.
Exactly. How much does the acid or base break apart into ions when you put it in water? Strong acids, think hydrochloric acid, sulfuric acid, they dissociate completely, 100%.
Every single molecule breaks up.
Yep. Every HCl molecule donates its H plus to water, forming H3O plus iron pluses. That's why they're strong electrolytes. Tons of ions are produced.
Okay. So what about weak acids then? Like vinegar?
Acetic acid, yeah. Or carbonic acid in your soda. Weak acids only dissociate slightly. Maybe only 1% or 5% of the molecules actually break apart at any given moment.
So most of it stays intact.
Exactly. Most of it stays as the original molecule. It reaches an equilibrium. There's a constant back and forth between the intact acid molecule and its ions.
Ah, equilibrium. We'll come back to that. So that's why vinegar doesn't, dissolve my salad bowl. Pretty much. It's just not producing that many H3O plus ions compared to a strong acid. Same idea for weak bases, like ammonia and window cleaner.
So strong bases dissociate completely too, like sodium hydroxide?
Yes, the common strong bases like NaOH or KOH break apart completely into metal ions and hydroxide ions, at very high concentration of OH.
Okay, that's why they're dangerous, found in drain cleaners.
Absolutely. They can cause severe damage because of that high OH concentration. Always handle with care. Weak bases, like ammonia, they're poor H plus acceptors. They only react partially with water, producing just a few hydroxide ions. Again, it's an equilibrium situation.
So this equilibrium thing, it sounds like a constant dance, this back and forth with weak acids and bases.
It absolutely is. That's the heart of reversible reactions. The reaction can go both ways. Reactants form products, and products can turn back into reactants.
So it never really stops.
Nope. Equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction.
The speeds match.
Exactly. So even though molecules are constantly reacting in both directions, the overall concentrations of reactants and products don't change anymore. They stay constant.
Like two water tanks connected by a pipe. Water flows back and forth, but the levels stay the same if the flow rates are equal.
That's a great analogy. Perfect. The levels are constant even though water is always moving.
And there's a principle that explains how this equilibrium reacts if you mess with it. Le Chatelier's principle.
Yes. Le Chatelier's principle is key. It states that if you apply a stress to a system at equilibrium, like changing concentration, pressure, or temperature, the system will shift.
Shift how?
It will shift in a way that relieves the stress. If you add more reactant, it shifts towards making more product. If you remove product, it shifts towards making more product. It tries to counteract the change.
Okay, it pushes back to find a new balance. How does this apply in the real world? Like maybe in our bodies?
Oh, absolutely critical in our bodies. Think about oxygen transport. There's an equilibrium between hemoglobin in your red blood cells, HP, the oxygen you breathe in, O2, and the oxyhemoglobin, HbO2, that carries oxygen to your tissues.
Hb plus O2 yields HbO2, kind of.
Basically, yes, and it's reversible. In your lungs, there's lots of O2, so the equilibrium shifts, right, forming lots of HbO2.
Makes sense. Loads up the oxygen.
But then, think about climbing a mountain. High altitude.
Less oxygen up there.
Right, less O2 pressure. That's a stress on the equilibrium. According to Le Chatelier, the system shifts left to compensate for the lower O2.
Meaning less oxyhemoglobin is formed.
Exactly, which means less oxygen gets delivered to your tissues. That's hypoxia.
Ah, altitude sickness symptoms. Headache, fatigue.
That's it. Your body feels that lack of oxygen. But over time, maybe 10 days or so.
You acclimatize.
Yes. Your body adapts by producing more red blood cells, which means more hemoglobin. More Hb shifts the equilibrium back towards the right, allowing you to carry enough oxygen even with lower pressure. It's Le Chatelier in action, driving adaptation.
Wow. Okay. Before we get fully into measuring acidity, let's talk about water itself. You said it's amphoteric.
Yes, water's fascinating. It can act as an acid or a base. In fact, water molecules can react with each other.
Water reacts with water.
Yep, a tiny amount does. One water molecule donates an H+, acting as an acid, to another water molecule acting as a base,
Forming.
forming a hydronium ion, H3O+, and a hydroxide ion, OH. This is called the autodissociation or autoindolization of water.
Does much of this happen?
Very, very little. In pure water at room temperature, the concentration of H3O+ and OH is only 1.0 by 10 to the 7 molar each. Tiny, but equal.
Equal amounts. So pure water is neutral.
Exactly. And the product of these two concentrations, H3O+ times OH, is always a constant value at a given temperature. We call it Kw, the ion product constant for water. It's 1.0 by 1014 at 25 degrees C.
Always 1018.
Always. Which means if you know the concentration of one ion, say H3O+, saying, you can always calculate the concentration of the other, OH. They're inversely related. If H3O+ goes up,
OH must go down to keep the product constant.
you got it. And that relationship defines acidity. Acidic solution, H3O+ OH. Basic solution, OH, H3O+ neutral. They're equal.
Okay, so we have these tiny concentrations, but the pH scale we always hear about, that's the more common way to talk about this, right? How does that work?
It is. The pH scale is just a more convenient way to handle those really small H3O+ concentration numbers. It avoids dealing with negative exponents all the time.
Easier to say pH 7 than 1.0 by 10 to 7 molar H3O plus.
Much easier. The scale typically runs from 0 to 14, and the definition is pH equals in molar deg H3O plus S, the negative logarithm of the hydronium ion concentration.
Well, right. Okay. So neutral pH is 7. That comes from the log of 10 to 7.
Exactly. Managed log 10 to 7 is neutral. Below 7 is acidic.
Lower pH means more acidic.
Correct. More H3O plus S, and above 7 is basic, meaning less H3O plus, and therefore more OH.
And because it's logarithmic, a change of 1 pH unit is a big deal.
Huge deal. It's a 10-fold change in H3O plus concentration. A solution with pH 3 has 10 times more H3O plus than one with pH 4, and 100 times more than pH 5.
Wow. That really puts things in perspective, especially for biology.
Absolutely. That's why even small pH shifts in your blood are so dangerous. pH is critical everywhere. Food safety, agriculture, environmental monitoring like acid rain, even the products you use.
How do we measure it? Litmus paper.
That's one way pH paper indicators give you a rough idea using color changes. For precise measurements, scientists use electronic pH meters.
Right. And you mentioned stomach acid earlier. It's like pH 1.5,
Right.
super acidic. How does the stomach handle that?
Yeah, it's incredibly acidic. Specialized cells called parietal cells pump out HCl. This low pH does two main things. It activates enzymes like pepsin to digest proteins, and it kills off most harmful bacteria in your food.
A sterilizer and digester in one. But why doesn't it digest the stomach lining itself?
Good question. The stomach lining protects itself by secreting a thick layer of mucus. It forms a barrier against the acid. It's a pretty robust system, but things like stress can actually trigger excess acid production.
Ah. And then when food moves out of the stomach.
As the acidic contents move into the small intestine, specialized cells there release bicarbonate.
Bicarbonate again.
Yep, the body's go-to neutralizer. It neutralizes the stomach acid, raising the pH back up towards neutral so the intestinal enzymes can work properly and the lining isn't damaged.
Okay, now we understand acids, bases, pH, strength. How do they actually react with other things?
Well, a few key reactions. Acids react with many metals like magnesium, zinc to produce hydrogen gas. You see bubbles.
Fission?
Exactly. And acids react with carbonates and bicarbonates like baking soda, sodium bicarbonate, or limestone, calcium.
What happens there? More fizzing.
Lots more fizzing. That reaction produces carbon dioxide, gas, water, and a salt. It's the classic volcanoscience experiment reaction, vinegar, acetic acid plus baking soda.
Right, okay. And the big one, acid plus base, neutralization.
Neutralization, that's the core reaction. Acid plus base, salt plus water. Hydrochloric acid plus sodium hydroxide gives sodium chloride, table salt, and water.
Simple enough. What's happening on the ion level?
The real action is the H plus from the acid reacting with the OH from the base. They combine to form H2O, water. That's the net ionic equation for strong acid, strong base neutralization. H plus OHT, H2O.
And in the lab, chemists use titration to measure this.
Yes, titration is how you find the exact concentration of an unknown acid or base solution.
Yeah.
You carefully add a known solution, the titrant, to a measured amount of the unknown solution.
Using an indicator.
Right, you add an indicator, like phenolphthalein, which changes color right at the neutralization point, the endpoint. By measuring exactly how much titrant you needed, you can calculate the unknown concentration.
Precision work. Okay, speaking of neutralization, let's talk antacids. How do they actually stop heartburn?
They are literally neutralizing that excess stomach acid, the HCl. They contain basic compounds. Common ones are aluminum hydroxide, magnesium hydroxide, those are often combined, calcium carbonate, like in Tums, or sodium bicarbonate, though that can release gas.
So they just react directly with the HCl?
Exactly. They provide a base, like hydroxide or carbonate, to react with the H plus from the stomach acid, raising the stomach pH and providing relief. Different ones have different side effects, though.
Right, you mentioned constipation or laxative effects.
Yeah, aluminum tends towards constipation, magnesium towards being a laxative. Calcium carbonate can raise blood calcium. Sodium bicarbonate adds sodium. So you choose based on what works and what side effects you want to avoid.
Okay, so the stomach is super acidic, blood needs to be incredibly stable. How does the body manage that tightrope walk, especially in the blood?
That's where buffers are the heroes. Absolutely essential.
Buffers, what are they exactly?
A buffer is a solution that can resist big changes in pH, even when you add small amounts of acid or base.
How do they do that? Magic?
Chemical magic, maybe. They consist of a pair, a weak acid and its conjugate base, or a weak base and its conjugate acid, working together.
Like the acetic acid acetate example.
Perfect example.
Oh.
If you add some strong acid, H plus, to that buffer, the acetate ions, the conjugate base, gobble up the added H plus, preventing the pH from dropping much.
Well, if you add base.
If you add base, OH,
Right.
the acetic acid molecules, the weak acid, donate their H plus to neutralize the added OH, preventing the pH from rising much.
It works both ways.
Clever. A chemical shock absorber.
That's a great way to put it. It absorbs the stress of added acid or base.
And our blood uses this to stay between 7.35 and 7.45.
Critically important. That range is non-negotiable for your cells to function. Below 6.8 or above 8.0, that's usually fatal.
Wow. So what's the main buffer in blood?
The primary one is the carbonic acid bicarbonate buffer system. HgCO3 is the weak acid, and HgO3 is its conjugate base.
Carbonic acid and bicarbonate. Those sound familiar. They should. Carbonic acid is formed from CO2 dissolved in your blood. So this buffer system is directly linked to the CO2 levels in your body, regulated by your breathing in your kidneys.
Which brings us right back around to Larry in the ER.
Full circle. His blocked airway meant CO2 built up in his blood.
Okay.
More CO2 means more carbonic acid, H2CO3. That equilibrium shifted right, producing more H3O plus ions.
Driving the pH down, acidosis.
Respiratory acidosis, yes. And the bicarbonate IV they gave him, that added more conjugate base, HCO3.
So the added bicarbonate soaked up the excess H3O placebo.
Exactly. It neutralized the excess acid, shifting the equilibrium back to the left, consuming H3O plus, and raising the blood pH back towards normal. A direct application of buffer chemistry and Le Chatelier's principle saving a life.
Amazing. It really highlights how delicate that balance is and how disruptions, acidosis, or the opposite, alkalosis, need quick correction.
Absolutely. Whether it's respiratory issues, kidney problems, diabetes, they can all throw off this crucial acid-base balance.
So today we've really journeyed from, well, sour lemons and slippery soap, all the way to the intricate chemical balancing act happening in our blood every second.
We have. We've seen how Arrhenius, Brunstad-Lowry, dissociation, equilibrium, pH, neutralization, and buffers aren't just textbook terms. They explain digestion, how we breathe at altitude, how antacids work, and even ER interventions.
It drives home that chemistry is fundamental to life science, to health.
It truly is. Every breath, every meal, it involves this incredibly delicate chemical dance to maintain homeostasis, that internal balance. Chemistry is, in a very real sense, the language of life.
So here's something to think about. Our bodies have these amazing, finely tuned buffer systems working constantly. But what happens if they're always under stress? What if things like chronic air pollution or maybe really extreme diets are constantly pushing those pH limits?
That's a really important question.
Are there other everyday exposures, maybe things we don't even think about, that could be subtly messing with our internal chemical balance over the long term?
Definitely food for thought. How resilient are these systems to constant low-level challenges?
Indeed. Well, thank you for joining us on this deep dive into the chemistry within. Until next time, keep that curiosity flowing.